So guess what? More 5.2. It is a chunky section. So we're going to continue talking about volumes of solids. Now the only difference is we're going to talk about the disk method, but in the idea of a rotation around the y-axis. So you're seeing, something like this. So it's just more like you're looking at curves, and then what happens if they rotate around the y-axis, and that is a different rotation than around the x-axis, because obviously you've got functions and you've got curves. And you can see, however, that it's still the idea of, for the disk method, slices that are circles. So we're adding up a bunch of these circles, just like we did before. It's just now we have a different orientation. So other than that, it is still the idea of pi r squared. It's just that the radius of this is going to be a distance like this instead of a distance like this. Okay. The washer method as well, very similar. You're rotating around, but you have an outer function and an inner function, and you want to take away that volume on the inside so that you're left with the volume that you're being asked to find. So very similar, again, just different orientation because we're talking about curves now. All right, so let's take a look at an example here. So we have a couple different functions here. Sorry, I have the wrong page. Okay. Okay, so sometimes just know that all we're going to do is set up an integral. We don't need to evaluate all of them. And even on quizzes or exams, I may ask you to do some sort of setup without actually doing the complete evaluation, because that really is the most important part, and then it becomes problems like we saw back in chapter 4. So we have a region bounded by y equals x cubed minus 8, and y equals 9 minus, and then in parentheses, x plus 2 squared, and the y-axis. So notice what's going to happen is that solid that you see, this piece here, is being rotated around the y-axis. So we have to think about, first, a couple different options. You can think about really the fact that because you're talking now about the rotation around the y-axis, that you need to have dy, and that means that your functions need to be in terms of y. So this function here, you probably, hopefully notice, is the upside down parabola. So y equals 9 minus x plus 1 squared. And then this other function way down here is, you can see it's a cube root function, but it's been shifted down. So y equals x cubed minus 8. And so what happens here is this piece gets rotated around here. Okay. And then down here, it's a different function. Notice that what's happening above there from 0 to 8 is different than what's happening from negative 8 to 0. So this is now a parabola. And again, kind of hard to draw, but the idea is you're looking at a disk method here, because this is completely, each of these slices is a circle. However, again, key thing to see, you should have two different integrals in this case. So we want to make sure that we have them in terms of x. So let's take y equals x cubed minus 8. That is the same as y plus 8 equals x cubed, and therefore the cube root of y plus 8 equals x. All right, so that's this function down here. And then our other is y equals 9 minus x plus 1 squared. So to solve that for x, again, this is needed because we're taking an an integral with respect to y, we'll have y minus 9 equals negative x plus 1 squared. Then we will multiply through by a negative, so we'll have 9 minus y, x plus 1, and always welcome to pause it and see what you get. So now I'm going to have a square root, 9 minus y, x plus 1, and so x is going to equal the square root of 9 minus y minus 1. Okay, and then this is not the washer method because this is a solid piece, but what I was saying earlier was when you go from negative 8 to 0, that's this bottom volume down there because of the the cube function that we then solved for x. So we need our pi, and then every disk, notice every disk has the radius of this. So written in terms of x, that is going to be the cube root of y plus 8, and then because we're trying to find the area, that's radius squared times pi, and that's going to be dy. So that's the first piece. And then the second piece is the integral from 0 up to 8, and again with our pi, we're going to see that we have this top function here that has been revolved, and so it's that solid, and then the radius of that is simply what we have here, but that distance needs to be in terms of x. So we'll have the square root of 9 minus y minus 1, and that will be squared, and that will be dy. So all we're going to do is just set this one up. You can find it and evaluate, but the important part is to know how to set up for a lot of these. So that's all I'll do. Let me write, let's see what kind of space I have. So now we'll do a couple more. We're still just going to do the setup. That is the hardest part. The actual evaluating is typically easier. Good practice, but easier. So now we have no picture. So we have the region y equals 1/3 x and x equals y squared, talking about that within the first quadrant. So we're just in the first quadrant of the axes. So the intersection points, if x equals y squared, we could also change this to x equals 3y, so that we have 3y equals y squared. That's going to give us y squared minus 3y equals 0, or y equals y minus 3 equals 0. So either y equals 0, y equals 3. If y equals 0, then that means x equals 0. If y equals 3, then x equals 9. The 1/3 x will be, if you put in 3 for x, you'll get 1. If you put in 6, you'll get 2. If you put in 9, you get 3. So we have this line here. And then if we do x equals y squared, if we put in, say, 4 for x, or, I mean, you could do anything. You could put in say 2 for y, you'll get x is 4, and obviously we know we're going to hit there. That might be really all we need. So 1, you know, we'll get 1. So it's going to give us something like this. Okay, but what we're doing with this is we are rotating it around the y-axis. So it's now going to come out here, and it's going to keep coming out here. And then this piece, you know, is going to come out, you know, so it's going to reach out that way. And then what we're doing, of course, because that's just on the other side to kind of show that this whole thing is then being rotated. And so there's going to be some aspect of, you know, the washer situation that's happening here. So we have kind of a washer situation, not kind of, we have a washer situation. So all we need to do with it, we're just going to do, you know, a setup here, is we're going to have the understanding that we're integrating our values of y, that if it's around the y-axis here, we're going to go from 0, 0 up to 9, 3. And so we're integrating from 0 to 3. But this is a washer method. We have an outer and we have an inner. And so we do want them in terms of y. So we have one of them. We have the inner one, the x equals y squared. The outer one is, so this is x equals 3y. This here is x equals y squared. So the outer function is always the x equals 3y. So when I think about doing the outer circles, that's pi r squared, where the outer is 3y. And then we want to subtract what we have on the inner, which is the y squared, and then that is with respect to y. So we could do another line here and just take a look at what it looks like, but we'll have 9y squared minus y to the 4th dy, and of course a fairly simple and straightforward integral to integrate. But that's all we have, and that'll give us the answer. Now, in contrast, we have the same exact thing, but we're being asked what would happen if we revolve that same region around the x-axis. So I want to show you the difference here. So we have this, we have 2, 1, 1. Okay, so we have our line, so it's the same region. But now what's happening is we're rotating around the x-axis. So it comes down here, and then we have our outer piece, 4, 2, 1, 1. Looks like this. And then this is getting revolved around the x-axis so that we have a bunch of washers in this direction. And, you know, so it's that idea. Ooh, picture's not great, but there we go. So a bunch of those. So it's still the washer method, but now what I want you to see is now we're looking at it in terms of integrating. So here, 0, 0, and up here, of course, we have 9, 3, but now we're integrating with respect to x. So we're adding up a bunch of these washers with a width of dx, change in x. But now I want you to see that our outer function is the x equals y squared, or y equals square root x, while the inner function, the inner radius, the height of that inner radius, is the y equals 1/3 x. And so that changes our integral up here. So in this case, we still have, it's still the washer method because it's still outer minus inner so that we don't get any of that inside. We're going from 0 to 9. And then outer squared minus inner squared. Think about what's going to go in there. So our outer is square root of x, again because we're in the first quadrant. Our inner is 1/3 third x. And both of them are squared because this is the washer method. So I'll just simplify that a little bit. We have x minus 1/9 x squared dx. And again, a fairly simple integration that you can find and get, no problem. And that's a couple examples of what it looks like to do around the y-axis, and then, you know, in contrast, what it would look like to take the same piece and rotate it a couple different ways. We're going to be finding the volume of something called a wedding band, which basically just means we're going to be looking at kind of a piece that then gets rotated around so it looks kind of like a ring. So it's found by taking the function f of x, which is a up like a cup parabola, and g of x, which is a down like a frown parabola, and it's actually going to get rotated around a horizontal line. So it's not going to get rotated around the x-axis. We'll be rotating it around the line y equals -3. So first thing I'll do is I'm going to graph this. So intersection points, I'll have x squared plus 2 and 4 minus x squared. We get 2x squared equals 2, and we get x squared equals 1, and x equals plus or minus 1. So those are the x values. We can see if we plug them in, we're going to get 3. So we'll have 1, 3, and -1, 3. And then what we notice is this is just an up like a cup parabola with y-intercept 2. And here we have a down like a frown parabola with y-intercept 4. So what happens is that this is going to get rotated. So you might be thinking, you know, washer method, and that's great. But it is getting rotated around this line y equals -3. So what this looks like is this. So you'll notice this is what we just graphed, and this is what it looks like when it rotates around the line y equals 3, y equals -3, and then that solid that's created looks like this last picture here. So the idea is if it was to be rotated around the x-axis, it would look the same but smaller because its radius wouldn't be as large. So the inner radius and the outer radius wouldn't be as long if it was rotated around the x-axis. But because it's rotated around the line y equals 3, that extends the radius for both, and so it has, you know, there's more volume there because it's doing more going around this line. It's bigger that way. So the way that we think about this is, so I'll do this part and then I'm going to switch because I have more space on the next slide. So let's think of the radius of the outer function and the radius of the inner function. So this outer function here, we already said was the g of x, 4 minus x squared, and that our inner function, and that's because that's on the outside when it goes around, and the f of x here is actually the inner, which is x squared plus 2, and so that's going to be on the inside. But when we think about the actual radius of that, the outer is 4 minus x squared, but then that would be just from, you know, any point on that function down to here. But we've now extended that radius another 3. So it's really your radius minus the line of rotation. So minus a -3, or you could say, you know, -x squared plus 7, or 7 minus x squared. Same thing, however, for the inner function. So we have x squared plus 2, that's this distance always here, but then again we're extending that radius. So our inner radius will be this minus a -3, or x squared plus 5. So now we have our outer and our inner, And now it's just, you know, exactly what you would think. It's the outer. So basically you're creating, using the idea of the disk method here, of a bunch of circles with this radius, and then taking away what you get from those circles to then create the shape. So it's going to look like this. So we'll have pi. These are slices up and down vertical. So -1 to 1. And then we have our -x² plus 7 squared. So that's the pi r squared for the outer, minus the pi r squared for the inner, x² plus 5 squared. And we are doing dx. Now, if anyone was thinking, hey, I feel like there was symmetry here because the on the y-axis, you might notice that both of those functions are even. So if you wanted to, if you think it might make your life easier, you could integrate from 0 to 1 and multiply your answer by 2. So that would be an option. So let me multiply out what I have inside. So I'm going to have x to the 4th minus 14x² plus 49. So I'm actually going to do this one, as you can see, minus, and then we have x to the 4th plus 10x² plus 25, and that's all dx. And then, so our volume here, then we can do some simplification, which is nice. So notice those x to the 4th are going to be gone. It looks like we'll have 0 to 1 of 2 pi. So we'll have a negative, looks like 24x², and then plus 24, so 49 minus 25, like that. And sure, I mean, you have options here. If you wanted to pull out the 24, you could do that. You know, it's up to you. Or you can just take your antiderivative like it is. So we'll add 1, we'll have x cubed, and then of course dividing by that will give us a -8. And then we'll have plus 24x, and that's going to be evaluated from 0 to 1. So luckily, putting in, you know, 0 is not going to be an issue, so we just need to put in 1. So we put in 1 and we get -8 plus 24. And that's going to be 16 times 2 pi, or 32 pi. And it does say find the volume, so we'll say units cubed. So that was an example of rotating around an axis of rotation. One thing I do want to mention is that notice we subtracted a -3. And the reason why that's important is because if, say for example, and I'm just going to draw on this, but know that this is not part of the problem that we just did, if you had instead this line, y equals 1, you notice that that actually makes the radius shorter because you're not even reaching the x-axis to rotate around. So in that case, you would just take your function, say 4 minus x², and you would subtract 1. So I'm subtracting -3, which is what elongates this radius. So you have to think about it as subtracting your line of rotation, paying attention, you know, to what that is. Is it decreasing what the radius is going to be? Is it increasing?